Howdy folks, welcome back to Advent of Code 2024. We are looking at day 10. This one is interesting. So, you arrive at the facility on a floating island in the sky. Woo. There's reindeer. It's cute. Apparently they're small enough to boop your leg. They have the Lava Island hiking guide. Most of it has been scorched by lava. Well, that's kind of what you get. Um, they also bring you a blank topographic map. Basically, they want you to fill in the missing hiking trails. So each map, each cell on here tells you the height of each position using a scale. So here is the top of the mountain, here is roughly the bottom. You determine that a good hiking trail is as long as possible and has an even gradual uphill slope. Hiking trail is any path that starts at height 0, ends at height 9, and always increases by a height of exactly 1. So we got 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 would be 1. Or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's actually, I think, 4 specific trails here. The reindeers helpfully began to do a bunch of stuff that we don't actually need right now. Trailhead is any position that starts 0 or 1 or more hiking trails. Here, these positions always have height 0. Assembling more fragments of pages, you establish a trailhead score is the number of 9 height positions reachable from that trailhead via hiking trail. So number of positions, not like... So I guess this one, even though we can trace multiple trails to get to this one place, it still has a score of 1 because it can only reach one specific position here. Single trailhead, oh yeah, and the above example has a score of 1 because it reaches a single 9. Okay, this one has a score of 2 because it gets 2 specific. Okay, this trailhead has a score of 4 because every 9 is reachable via hiking trail except one immediately to the left. Okay, so yeah, I can't get to that one, but I can get to this one, and this one, and this one, and this one. There are 2 trailheads. The trail at the top has a score of 1, with the trailhead at the bottom is a score. It's because this one cannot go down. We can't go down on a trail because that's not how hiking works. We can go here, and this one can go here and to this one. Okay, and this has 9 trailheads, and then basically how many trails can each of these trailheads reach? La-di-da. Okay. Let's start with this larger example just because, it's nice to have the bigger example. I've already pulled in some code from a previous one that just pulls in maps and splits them and parses the int, so we should be good to go with that. So the idea here, we have this map, we got to find all the trailheads. So there's a couple ways that we can handle this. One is we could actually handle, if we wanted to do this in like this kind of the cheap way, we just do it as we did before, just recursive. We hit this, we know it can go here. If we want to do this more interesting way, we could actually create a graph out of this, because we know that elements can only connect to elements that are one step higher than them. So we could create a graph of all the elements, and like that just makes later computations easier. I don't think for what we're being asked to do right now, I don't think it actually makes things too much easier, but it's something to keep in mind for later. Okay, so what we want to do, first of all, let's just loop over everything. Basically, I could have something that's looping over here and finding the trailheads. I'm just not going to worry about it. Let y equals y less than map dot length. All right, that's wrong. For let x equals 0. Okay, that is definitely not what I want to do. So, okay, so what we're going to do here, num equals map y x. If num equals 0, then we may begin. So if number equals 0, then we're going to start off our check. And so what I want to do here is I want to actually recurse from this point. So we're going to make a function, find trails xy. Okay, so that's basically find all the trails from this point onwards. And so then trails found equals find trails X and Y. Essentially that. So yeah, the idea here is that when we go to look for these trails, we're going to start from this coordinate, and then we're going to look around us and find all the positions that we could step to from our current coordinate, the orthogonal ones. And then from those, we're going to recurse onto all of those. And if any of those end up at a 9, they will report back and say specifically which 9 they got to. Because that's important, because if we get to the same 9 multiple places, then, we don't really care that much. So let's see here. First of all, we have to find out where we are so that we know what we could possibly handle. Neighbors equals, so this is actually going to be x minus 1 y, and then x, y minus 1, oops. And then that actually looks right, yeah. So each one of these is a potential neighbor of this point. Const neighbor of neighbors. And we're going to loop over all of these. This might actually work. If height less than equal, no. Actually, so what we're going to do, this is mostly correct, but we're actually going to say if height equals my height plus 1, because that's the only way that we're actually allowed to step onto that trail. So if it is the case that that's there, then we want to find trails of nx and y. And actually, this is kind of wrong, because this is also off x and off y. It's not the actual... oh no, it is, because, okay, never mind. It is actually, it's not the offset, because I'm actually getting the real coordinates here. Okay, so that's the result. What we're going to say here then is if my height equals 9, this is our end case. This is when the recursion should stop. We're going to return a single array, an array containing that coordinate pair, saying that, hey, we have found, you know what, let's use this as a key, actually. Because then I don't actually care which, after this, I don't care which ones I found. I just care that they exist. And you know, let's use a set. Because a set cannot contain items, like it has to have unique items. So let's do this. Let's do a set. Okay, result equals, const result equals new set, and then for here we're going to say for result, I could have called this all result too, and that might have been better. We're going to say this is actually item result dot add item. Now this is not push, because sets are technically not in any particular order. And then return result. All right, so let's just see. Let's just run this for 1, and I want to just see what it comes up with. Terminal, and then part 1. Let's see what we get. Okay, it did not loop forever, so that's good. All right, here's our original map, which I don't know if I need, but the first 0. Okay, firstly, it's hitting 0, 1, 2. It hits this 1. Okay, then it hits 1, 0. That is oh no, that's the 9 that it hits. Okay, it hits 0 and 3. Okay, so it hits this one, supposedly. It can get to this one, can it? So 0, 1, 5, 6, 6, 7. Yeah, okay. Okay, so this one basically can get to 5. if we get bugs, I'll pick a simpler sample because this one's actually kind of hard for me to figure out. You know, hmm. If we really need to debug it, what we also could do is instead of just returning this, we actually unwind the path that it took, and that could be useful as well. So then this means this trail, total trails equals 0. Let's go. Total score, actually. So this thing's score is actually going to be trails found dot length or dot size, whichever. And dot. I'm just going to assume there's a length on here. And let's just see if that works. Not a number. Well, that's great because I bet length, I bet it is size. There we go. So that's 11. 36 is what we're getting here. Okay, this is 9. Oh, you know what? Because I did a bunch of breaks. That's why. Let's not do the breaks then. Okay, 36. I'd be really suspicious if this just worked because I just threw this together really fast. But let's take a look. Let's get our actual input. Okay, significantly longer. Pop that in there, and let's just see what we get. $694. No, not this. 694. Oh, okay. Well, that was the answer then. Okay, so let's take a look at our, not that, at our algorithm. So, first of all, we're pulling in our map, pretty standard, getting just a nested array of integers. Then we have our recursive function, which takes in coordinates, figures out the height. If our height is 9, then we're done. We just return a set containing our own coordinate pair. Then we figure out our neighbors, look at our neighbors. If any of our neighbors, well, first of all, make sure our neighbor is on the map. See, very appreciative of that. Then we figure out the height of our neighbor. If our neighbor is one height above us, it means we can hike there. And so then we recurse onto that neighbor. The thing that you might run into here, though, is infinite loops. Luckily, we didn't have any here. So if you're recursing onto your neighbors, basically, in this case, all trails lead somewhere. There's no case where there's a 7 that just doesn't go anywhere at all. Well, no, I guess that makes sense. We can't infinite loop because we've got this height check. That's why. Because I was thinking like, oh, we don't actually have any. But yeah, we can't. If something's going up in height, then inevitably will go to 9, or it'll just end and have no places where the height is greater than 1, or 1 greater than it. So that should be fine. So we add that all in. We combine those sets, which are unique. So if we get to a certain point multiple places, we don't really care how. Then we get our score. We just figure out how many trails we found for every 0. Basically, look through the whole map, get every trailhead, find out how many trails we found, tally them up, and that's that. So let's take a look at part 2. Realizing something. Okay. Rating. Trails rating is the number of distinct hiking trails which begin at that trailhead. Okay, so this is the different ways that you could possibly get to that 9. Okay, exactly 3 distinct hiking trails begin at that position. Rating 13. Single trail rating 220 because there are 121 distinct hiking trails that lead to the 9 on the right edge. 106. Yeah. Large example from before, they have ratings of here. The sum of the ratings is 81. So, what is the sum of all the ratings of all the trailheads? This is important now because now when we're looking at this, we have to know all the different paths we went down. Not just the trailheads that we hit. And actually, we don't anywhere care about the trailheads that we hit. So now what we get to do is we get to actually return. Okay, so here is, we get to return 1. Because at this point, we've got 1. Okay. Now, let's say we get a child result. That's going to be a number. We are actually going to add to our own result. Okay. This way had a certain number of ways to get here. So let's see. We need a total sum here. So this is actually going to be, we add on plus equals child result. Okay. plus 1. So then let's say if we had a 9 surrounded by 4 8s, well, no, actually, what's a better way of doing this? If we have a neighbor that has 4 9s surrounding it, that particular thing would have a rating of how many different trails? That'd be, no, we only, oh, okay, we only do actually want to add the child result. We don't want to add plus 1 because that is the individual trail. This will start off at 1, right? Okay, and then it'll split based on that. And why are you? The fact that's colored differently concerns me. Because that means that something has gone wrong here. See, looking at your color coding can be really important here. Total trails. What did I do wrong here? I'm gonna just run this and it'll tell me. Oh my gosh. I'm also realizing I need to put a part 2 on this. Let's do that, and let's undo a bunch of changes on this one. There we go. I think that does it. Okay, cool. So now part 2. Result is not defined. I'm 44. Oh. Maybe that's the issue. Oh, now it's working. That looks fine. Okay. Total trails. Okay. Now I think, let's see what this gives us. 81. 81. Okay, well, let's try it with our input. Okay, 1497. Oh, 147. Oh, cool. Well, that's surprisingly easy. Okay, well, let's talk about this algorithm real quick. So, same thing here, pulling this in. Our find trails now, if we find a 9, it returns 1, which means we've got one step on the trail, or one trail that gets to a 9. The fact that we're doing this total trails plus equals child result means that we're basically saying, well, how many trails did that child step have to get to a 9? And then we add that, which means that we are the sum of all of the trails our children could get to. Which means that when it gets all the way down to the base case, that zero has that recursive sum branching of all the trails. And then we just sum them up like normal. Okay, cool. That was a little bit easier than I thought it was going to be, but recursion. Again, you don't have to do recursion with this. You could do something with like a queue, but recursion often makes things like this a lot simpler. Anyway, I hope this is interesting, folks. I'll see you next time.